Okay guys, this video is going to be for what I have on my lesson plans that I posted on Google Classroom for today, which well actually it's posted for tomorrow, so this will be for tomorrow and Wednesday, Tuesday and Wednesday this week. Before we get into this, I just wanted to kind of explain things. I posted a message today. I hope you saw that. There is a survey that I'm wanting you to complete to tell me whether or not you are going to be wanting paper copies. Everything that you'll need for class will be posted on Google Classroom, just like I always do. But if you will still want paper copies, you do already have paper copies in your binder for this unit. If you will continue to want paper copies, you'll have to fill out that survey and let me know that so that I can make sure that we can get paper copies to you. We'll have to make arrangements for that, and we'll let you know the arrangements for that later. Also, I did talk to Miss Emberton, and your binders are here at school in my room, so if you would like to come up here Monday or Tuesday this week, that is the 16th and 17th of March, between 8 and 2 p.m., someone will be here to let you pick up that binder. Also, on the survey, I will be asking you to let me know whether you would rather do videos like the one that I'm doing now, or whether you would rather have live class. We can do live class on a platform like Google Meet, where I would be on there, you guys would be on there with me, and I would go through things with you. I can show you my screen and go through things with you, and you could ask questions if you need to. The main issue with that would be that we would all need to be available at the same time on the same day so that we could all have class together, because I can't, it would take a lot of time on my part to have to make a lecture for those who couldn't be present at the live lecture, to have to make a lecture video for those people and then do the live lecture as well. So that would be like me doing double the work. So if we can all agree that on a certain day and time that we could do a live lecture and you guys would want to do that, that would be perfectly fine with me. Otherwise, we will continue to do the videos like I'm doing right now. The advantage of the videos is that you can watch it whenever you have time and do your work. Also, if you have questions as far as maybe you didn't understand, you can rewind that video and watch it again, or you can pause it and try to do something on your own and then start it again. So you have a lot of control over what you're watching and how often you watch it and when you watch it. But again, if you would be interested in the live lecture, again, you can indicate that to me on that survey, and then we'll look and see if all 4 of you are interested in doing the live lecture. Then we can try to schedule a day and time to do that at least, once or twice a week. Right now, we're out for 2 weeks. Who knows if it will be just 2 weeks or if it will be longer than that. We just don't know, so we're just going to have to do the best that we can with what we have right now. Also, a little bit about how we're going to do this. It's going to be very similar to what we were doing when we were here at school, except for the fact that you'll be online and you'll be watching videos, or we'll be doing live lectures, whichever you want to do. But we will, still do practice problems, and then you'll have some that you'll have to do and turn into me, which will count as your homework. Again, with the videos, I will put assignments up where you will actually work out the problems and submit your work to me. So to submit your work, I know it's going to be hard to type in all these calculations, so you can do the work on paper, you can take a picture of the work, and then you can insert that work into a document that I will put on Google Classroom. Again, I will probably give you, 2 or 3 assignments each week. Some of that will be an actual Google assignment where it will have a document where you can take pictures of your work and upload it. Others may be like a Google form quiz or something like that. But you'll have 2 or 3 assignments a week, and they will be due by 11:55 on Friday night. So they will be due on 11:55 on Friday night of the week that those assignments were posted, and I will try to make sure to put that note on every assignment that I do send to you. So I think I've gone over just about everything in the message. If you have any questions, feel free to email me. Also, I did forget to say that whether we're doing videos or live lectures, if you have a question, I'm available. I'm here to help you. So just send me an email, and if I can't answer your question in an email, then I will email you back, and you can send me your number. We can do a phone call. We can do FaceTime. We can do Skype. We can do, whatever it is that you need to help you understand what it is that you need to know as far as the content goes. So I just wanted to kind of put that out there as well, that I'm always available, during the day for any questions that you have or any help that you might need, so that you don't feel like you're out there all by yourself, because you're not. I'm here with you, and all you have to do is let me know. All right, so last week on Wednesday, we began talking about the combined gas law. Remember, the combined gas law is P1V1 over T1 equals P2V2 over T2. Remember that the temperature must be in Kelvin, and to change it from Celsius to Kelvin, we have to add 273. Remember that the units on both sides must be the same. So if our volume is in milliliters on one side, then it has to be in milliliters on the other side. The same is true for pressure. Whatever unit you have for pressure must be the same unit on both sides. And remember, I told you that you could use this combined gas law and not only use it on a combined gas law problem, but also on any of the other problems that we've done up to this point: Boyle's law, Charles' law, or Gay-Lussac's law. So what we're going to do first is we're going to do another example or two using the combined gas law, and then we're going to go back and look at some of those Boyle's, Charles, and Gay-Lussac's laws and see how we can use the combined gas law on those as well, by just marking out the variable in that problem that is constant. So let's go ahead and look then at number 3. Now again, this is in your packet for this unit, Unit 4, the gas laws, which probably is here at school. So I do have it posted on Google Classroom. So if you can print it out from Google Classroom, then that is awesome. Otherwise, you'll have to write it down on a piece of paper, or you'll have to come to school and get your binder so that you'll have your packet that I'm working from. Looking at number 3, a gas that has a volume of 28 liters, a temperature of 45 degrees Celsius, and an unknown pressure, has its volume increased to 34 liters and its temperature decreased to 35 degrees Celsius. If I measure the pressure after the change to be 2.0 atmospheres, what was the original pressure of the gas? Well, first thing when we look at this, we see that our temperatures are in Celsius, and we know that we're going to have to convert those to Kelvin. To do that, we have to add 273. So 45 plus 273 on our calculator, and I'm not doing that in my head, is 318 Kelvin. So that's that temperature. And then 35 plus 273 is 308 Kelvin. So we have to remember that those temperatures need to be in Kelvin. Okay, now that I have my temperatures converted to Kelvin, now I'm going to go through and start looking at what I'm given. What is my given information? So I have a volume here of 28 liters. It tells me the volume is, so I know that that's one of my volumes. I know that this 318 is one of my temperatures. I know that I have another volume here of 34 liters and another temperature here of 308 Kelvin. All right, so the gas, it looks like originally had a volume of 28 liters, so that's V1, and a temperature of 45. And its volume is then increased, so that volume would be V2, and then the temperature decrease would be T2. If the pressure of the gas after the change, okay, so this is the pressure after the change, is 2 atmospheres, so that would be P2. Then what was the original pressure of the gas? That looks like we're looking for P1. P1 is what it's asking us to find. So it looks like they've given us, originally we had a gas that has a volume of 28 liters, a temperature of 318 Kelvin, and we increase its volume to 34, so that is after the change, that's our V2. Temperature decreased to 35 or 308 Kelvin, that is our T2, because it's after the change. And then the pressure after the change is 2 atmospheres, so that's P2, and it tells us we're looking for the original pressure, which is P1. So what I'm going to do then is I'm going to take this combined gas law and plug in or substitute in my variable or my numbers for my variables. So P1 is what I'm solving for. V1 we see is 28 liters. And then T1 we said was 318 Kelvin. Okay, moving on, P2 we see was 2.0 atmospheres. And if you hear anything in the background, that is my child that's in my classroom with me, guys, because he is also out of school and he has work to do and he is over there working, but also sneezing and making noise. So if you hear anything, that is him. Moving on, V2 is 34 liters, and I need him to be quiet so that he doesn't disrupt this video too much. Okay, and then our T2 we calculated was 308 Kelvin. All right, so then we need to solve for P1. To solve for P1, we're going to have to multiply both sides by 318 Kelvin. And then we would have to divide both sides by 28 liters. The other way that you can do this is that you can actually work all this out first, and go from there. So I think that's what I did last week, and that's probably what I'm going to do today as well. So I'm going to we have P1 times, and then we're going to do the 28 divided by 318. And so that is going to be 088050314. Okay, and then on the other side we have 2 times 34 equals divided by 308, and that gives us, and again I'm not doing any rounding here because we're not getting a final answer yet. So now that I have divided 28 and 318, and then 2 times 34 divided by 308. Now I can solve for P1, and as you can see, I'm going to need to divide both sides by 0.08805,314 in order to get P1 on this side by itself. So the 088050314 is going to cancel out, and that's going to leave us P1 on the left, and on the right we're going to take our 0.220779221 divided by 0.088050314, and then I get 2.494591952, and again, since this is pressure, I know this pressure is in atmospheres. Since my other pressures in atmospheres, I know this one is in atmospheres as well. And then I have to look at my significant digits. It looks like 2.0, 35, 45, and 34 all have 2 significant digits. So this would round 2.4, the 9 rounds the 4 up to a 5, so that would be 2.5 atmospheres would be my final answer here. So again, the original pressure of the gas before the changes would have been 2.5 atmospheres. So again, it is just substituting in the variables. I think the hardest part here is identifying which variable is which, and making sure that you get the correct pressure, volume, and temperature on the correct side of the equation. Making sure that you can identify what was the original and then what is the new or the after the change, which would be the 2's. The 1's are the original, the 2's are the after the change. Okay, so let's look at one more example. A gas has a temperature of 14 degrees Celsius and a volume of 4.5 liters. If the temperature is raised to 29 degrees Celsius and the pressure is not changed, what is the new volume of the gas? Okay, again, I see that I have my temperature in degrees Celsius, so I am going to convert that to Kelvin. So 14 plus 273 is 287. Okay, and then 29 plus 273 is 302 K. Okay, so a gas has a temperature, so we know that that is a T, and a volume. Okay, so we know that that's a V. The temperature is raised. Okay, so again, if the temperature is raised, this means after we are changing it. So after the change, the temperature is the 29. So this must be then before the change. And the pressure is not changed. What is the new volume? So this must be V1, because at this original temperature, this is its volume. The new volume then is going to be V2. Notice that the pressure is not changed. So really, guys, what we're looking at here, when we have pressure constant and we are changing temperature and volume, that is really Charles's law that we're using here, but we don't have to remember Charles's law. We can use this combined gas law. So again, if we go back up here and we see that pressure remains constant, then we can take pressure out of the equation. So when we take pressure out, we have V1 over T1 equals V2 over T2. And if you go back, you see that is Charles's law. So if you have this combined gas law, you have all three laws, Boyle's, Charles, and Gay-Lussac's law in one. So what I'm going to do then, you don't have to do this on your paper, I'm just showing you what I'm doing. I'm just rewriting this combined gas law. And since pressure remains constant, I'm just getting rid of pressure. I don't need that in there because it stays the same. There's no point in putting it in there. We don't have to know what it was as long as it stays the same. Then doesn't matter. We can just take it out. And now what we have there is Charles's law. You don't have to know that, but this makes this problem a little bit easier. So then we've identified V1 as 4.5 liters. T1 we said was 287K. V2 is what we're solving for. And then T2 we said was 302K. So to get V2 by itself, we have to multiply both sides by 302. This cancels out. So on the right we have V2, and on the left we're going to take 4.5. And then you can multiply by 302 and then divide by 287, or you can divide by 287 and then multiply by 302. It really doesn't matter. I'm going to go ahead and do 4.5 divided by 287 and then multiply by 302. And I got 4.7351911638. Again, our original volume was in liters, so this is also in liters. Last thing that we need to consider is significant digits. Again, 14, 4.5, and 29 all have two significant digits, so we must round this to two significant digits. The 3 does not change the 7, so my final answer is 4.7 liters would be what B2 would be. So after we make the changes, we increase the temperature from 14 to 29 degrees Celsius, our volume increases from 4.5 to 4.7 liters, which makes sense. When we increase temperature, we should see an increase in volume as well. So again, as I told you before, go back and make sure that the answer that you're getting makes sense. If we're increasing the temperature, then we should be increasing the volume also, which we did. It went from 4.5 to 4.7. So if you'll take the answer that you get, go back and check and make sure that it makes sense for what you did, the changes that you made to the gas, then that will help you to be sure that you've pushed everything into the problem or into the calculator correctly, and it will also help you to make sure that you've substituted the numbers in the equations correctly. Okay, I'm going to keep using the combined gas law, and I'm going to do another problem here. It says calculate the final pressure in a scuba tank after it cools to 1.00 times 10 to the third degrees Celsius to 25 degrees Celsius. The initial pressure in the tank is 130.0 atmospheres. So again, P1, B1, T1 equals P2, B2 over T2. Okay. The final pressure inside a scuba tank, or calculate the final pressure. So we are looking for P2. That's what we don't know. Okay, that's what they're asking us to find. Calculate the final pressure. The final is P2. It's going to cool from the 1.00 times 10 to the third degrees Celsius to the 25 degrees Celsius. So its original temperature then must have been that one, and then it's cooling down to this one, which is T2. And then the initial pressure in the tank, so that's P1, is 130 atmospheres. Again, the other thing we need to do here is convert our temperatures to degrees, or to Kelvin. So 1.00 times 10 to the third, well, if you do 1.00 times 10 to the third, that is 1,000. Okay, we're just moving our decimal 3 places to the right. And then we have to add 273 to that. So T1 is 1.00 times 10 to the third plus 273. So basically you're doing 1,000 plus 273, which is 1,273K. And then T2, we're cooling it down to 25 degrees Celsius. So add 273, so 25 plus 273 is 298K, which is T2. Now, the other thing that we have here is we see we're talking about temperature and pressure, but we're not saying anything about volume. So then if it doesn't say anything about volume, then that must mean that our volume is remaining constant. So we can just mark volume out of our equation, and now all of a sudden we have Gay-Lussac's law. Now, if we go back and look on this sheet that I'm working on, it is Gay-Lussac's law worksheet. So again, if you know that combined gas law, you can use it to solve most of these problems, even though you may not know exactly which law it is that you're using. If you use that combined gas law and mark out the one that is remaining constant or the one that it doesn't give you the information for, then you know, then you'll have the equation that you need to solve the problem. So again, P1 we said was 130 atmospheres. T1 we said was 1273. P2 is what we're looking for. And T2 we said was 298K. So again, to get P2 by itself, we have to multiply both sides by 298K. Again, you can do cross multiplying. You're going to get this. You're going to do the same thing and get the same answer. So on the right we have P2. On the left we have 130 times 298 divided by 1273. And we get 30.43205027. Again, this is pressure. Since our original pressure was in atmospheres, that means this is in atmospheres as well. So last thing we do is look at significant digits. 1.00 has 3, 25.0 has 3, 130.0 has 4. So that means we need 3 significant digits in our answers. So 30.4, the 3 does not change the 4. So that's 30.4 atmospheres. Now, before we leave this problem, let's check and make sure it makes sense. If we're cooling it down from 1,000 degrees to 25 degrees, okay, so we're cooling it down a lot. The pressure has gone from 130, it looks like, to 30. So does that make sense? That if we cool it down, if we cool it down a lot, the pressure is going to decrease by a lot. And that should make sense to you, because when we cool a gas down, the particles move slower, which means they're going to hit the walls of the container less, and so we're going to have less pressure being exerted by the gas on the container. So yes, when we cool it down a lot, the pressure should decrease a lot. So I think we did that one correctly. If we look at another one here, again, just doing some different problems using that combined gas law. Again, I'm going to write that down so that I have it here in front of me. Okay, I've made a thermometer which measures temperature by the compressing and expanding of gas in a piston. I have measured that at 100 degrees, the volume of the piston is 20 liters. What is the temperature outside of the piston if the piston has a volume of 15 liters? What would be appropriate clothing for the weather? So we're going to figure out temperature by using this information here. So I have measured that at 100 degrees Celsius. Well, I hope we know that that is a temperature. The volume is 20, so that's a volume. What is the temperature outside? So we're looking for a temperature. If the piston has a volume, so there's another volume. So at 100 degrees, the piston is 20. So we're going to call those 1, T1 and V1. What is the temperature? So we're going to look for T2 if the piston's volume, V2, is 15 liters. Again, we really don't have necessarily an initial or a final here, but we do know that at this temperature it is this volume, so those two need to go on the same side together. That's why I named those 1. And then this is going to be my new volume, and I want to know what my new temperature is. So again, here we're using volume and temperature, so this must mean then that the pressure is constant. So if I get rid of pressure, then you can see I have V1 over T1 equals V2 over T2. So the next thing that we need to do is make sure that we convert our temperatures from Celsius to Kelvin. So T1 is 100 degrees Celsius. We have to add 273 to that, which gives us 373K. And then T2 is what we don't know. So again, when we do get our temperature, we know it is going to be in Kelvin because we're going to use Kelvin for T1. So V1 we said was 20. And you guys, I'm going to go ahead and put a decimal after that so that we don't have just one significant digit. I'm going to put a decimal after these. So 20 liters T1 is 373 K. V2 is 15 liters, and T2 is what we don't know. Again, since T2 is on the bottom, I think it's going to be easier if we do this one by cross multiplying. So we're going to cross multiply here. 20 times T2 is equal to 15 times 373. And then as we can see here, we're going to have to divide both sides by 20 liters. So on the left we have T2, on the right, liters will cancel out, and we will have 15 times 373 equals, divided by 20. And we're getting 279.75, and this is K. And again, it looks like we're going to need two significant digits because 20 with the decimal after it and 15 both have 2. 100 with the decimal after it has 3. So we're going to do two significant digits. So 279.75 is going to round to 280K as our T2. Now let's check and make sure this makes sense. If the volume goes from 20 to 15 liters, the volume decreases, then what should happen to the temperature? Well, we should see, again, this is a direct relationship. Lower volume, lower temperatures mean lower volumes. So if we have a decrease in volume, then we should expect that, hey, the temperature must have decreased, causing that gas to contract. You know, the particles are moving slower, so it's going to take up less space. Again, so the temperature should be lower, and it is. We went from 373K to 280K. Now, the other part of this question, what would be appropriate clothing for the weather? Well, do you know what 280K is? Okay, not really. Because I'm not used to Kelvin. So what I'm going to do is I'm going to convert this back to Celsius. So instead of, we add 273 to change to Kelvin from Celsius. So we're going to subtract 273 to change from Kelvin to Celsius. So minus 273, which gives us a temperature of 7 degrees Celsius. Okay, so 7 degrees Celsius, what kind of clothing would be appropriate for 7 degrees Celsius? Again, you can tell obviously that is probably a little bit cool. Now it's not 7 degrees Fahrenheit because that would be below freezing, but this is 7 degrees Celsius, which for comparison, normal body temperature, 98.6 degrees Fahrenheit, is about 37 degrees Kelvin. So this is 30 degrees lower than your body temperature. So definitely it's going to be pretty cool. And so we're going to say we probably need a coat, hat, and gloves if we're out in the weather where this piston has a volume of 15 liters. Okay? One more problem over this. Divers get the bends if they come up too fast because gas in their blood expands, forming bubbles in their blood. If a diver has 0.05 liters of gas in his blood under a pressure of 250 atmospheres, then he rises instantaneously to a depth where his blood has a pressure of 50 atmospheres. What will be the volume of gas in his blood? And do you think this will harm the diver? So again, we need to identify what we're given and what they're asking us to find. So a diver has 0.05 liters. Well, we know liters is a volume under a pressure of 250 atmospheres. So we know that that is a pressure. Then he's going to rise to where his blood has a pressure of 50 atmospheres, and we want to know what will be the volume. Okay, so again, initially it looks like he is at a pressure of this, so if that's P1, and a volume of this, and then he is going to rise instantaneously. So he's going to change his location in the water to where he has a pressure of 50 atmospheres, which is P2, and we want to know what will V2 be. Okay, so again, if we use P1, B1, T1, again, just using the combined gas law here, notice this is not saying anything about temperature in this case. So we're going to assume temperature remains constant, so it's not going to be part of our equation. We're going to mark it out. And what we have left is P1 V1 equals P2 V2, which again is Boyle's law. So substituting the information in, 250 atmospheres. V1 is 0.05 liters. P2 is 50.0 atmospheres. and V2 is what we're solving for. So again, to solve for V2, it looks like we're going to have to divide both sides by 50 atmospheres. Again, notice that the pressure is in atmospheres on both sides, so that it will cancel out. If it were not in atmospheres on both sides, then it would not cancel out. So you have to make sure you have the same unit on both sides. So what we're going to do then, 250 times 0.05 equals divided by 50. And that gives us 0.25 liters. All right, so again, looking at our significant digits, let's just go ahead and put an O here, because I'd like to have at least 2 significant digits. Put a decimal there, and then that means we have 3 significant digits, and if we put an O there, we have 2 significant digits. So we're going to leave it with 2 significant digits. So that is part of our answer. What will the volume of gas in his blood be? Well, 0.25 liters. Now let's make sure that makes sense. At this high pressure, he has a pretty small volume, 0.05 liters. But then when we go down to this, we come up in the water to a much lower pressure, so we've decreased the pressure by about 200 atmospheres. We see that the volume has increased. Do we expect when the pressure goes lower, the volume gets bigger? And yes, we should expect that. Remember, it's an inverse relationship. Higher pressure squeezes the gas together, so you have less volume. Lower pressure allows the gas to expand more, so we have more volume. So when we lower the pressure from 250 to 50, the volume comes up quite a bit, from 0.05 to 0.25. Now the question is, again, we're talking about the bends if they come up too fast, because the gas in their blood expands, forming bubbles in their blood. So if we increase the volume of gas in his blood from 0.05 liters to 0.25 liters, is that going to form a lot of bubbles? Yes, it sure is, because we've increased the volume of gas in his blood by about 5 times. And so, yeah, we're going to get a lot of bubbles, which can cause major problems in this guy. So do you think this will harm the diver? I would say yes, most definitely it's going to harm the diver. We're going to get lots of bubbles of gas in his blood, because we have that gas has expanded so much so quickly. This is the reason why when you're diving very deep, you have to rise slowly, so that your gas in your blood can become accustomed to the decreasing pressure as you come up, so that you won't have issues with lots of bubbles in your blood, because those bubbles can lead to aneurysms and strokes and things like that. All right, so that will be all for what I have on the Google Classroom for Tuesday. Now, we're going to go ahead and we're going to look at what I have on our lesson plans on Google Classroom for Wednesday, and that is the ideal gas law. So before we actually start working some problems with the ideal gas law, we're going to look at our PowerPoint. You want to write down in your packet what the ideal gas law is. Remember, there are 4 quantities that we use to describe gases. We've talked about 3 of those already: pressure, volume, and temperature. The 4th one that we haven't used until now is going to be the quantity or amount of gas, which we're going to be using in moles. And we know that we can convert between grams and moles. So if we have the ideal gas law, we can use relationships between pressure, temperature, and volume to help us calculate the number of moles, and then, of course, grams of a gas that we're using in our problem, using this ideal gas law. So this is the ideal gas law. We call this PIV-NERT. That will help you to remember that formula, PIV-NERT. PIV-NERT, okay, not pervert, but PIV-NERT. Kind of sounds kind of funny, I know, but the P in the PIV is pressure, the V in the PIV is volume, and then in NERT, the N is the number of moles of gas, the R is a gas constant, and of course the T is temperature. Again, the temperature must be in Kelvin. Now again, we're going to really look at this gas constant next, because this gas constant is going to determine what units of pressure, volume, and temperature that we're going to be using. There are different gas constants. The 2 most used gas constants, again, R is the gas constant, which we're going to call the ideal gas constant. So if you want to use your pressure in atmospheres, then your R is 0.0821. If you want to use your pressure in kilopascals, then your R is 8.314. And again, all the other units in the equation must match the units of R. So again, if we're using the pressure in atmospheres, then our R is going to be 0.0821. That is pressure in atmospheres, volume in liters, N in moles, and then temperature in Kelvin. If you want to use your pressure in kilopascals, then R is 8.314. Again, volume is still in liters, N is still in moles, and K is still in, temperature is still in Kelvin K. So again, the main difference in these two R's is the unit of pressure. And since we're using two different units of pressure, we have two different values for R. So again, make sure when you're doing your problems that your units in your problem match the units of R that you're using. Okay, so now we're actually going to use PivNert. Let me see if I can find what I'm looking for here. Here it is. No, it's here somewhere. All right, so again, here is the law, PV equals nRT, PivNert, and then here are our two gas constants, ideal gas constants. We just had 8.314, so I'm going to go ahead and put a 4 on that, and then 0.0821 if the pressure is in atmospheres, 8.314 if the pressure is in kilopascals. So let's look at number 1. If I have 4 moles of a gas at a pressure of 5.60 atmospheres and a volume of 12.0 liters, what is the temperature? So we're going to say 4.00 moles there, so that way we have 3 significant digits and everything. So again, my equation is PivNert. So I'm going to substitute in, okay, I have 4.00 moles. Well, which one of these is moles? Well, that is our N. We have a pressure of 5.60, so that is our P. We have a volume of 12.0 liters, so that is our V. And we're wanting to know what is our T. Now you can see here with PivNert, we don't have a P1, V1, T1, okay? We just have a pressure, a volume, a number of moles, a gas constant, and a temperature. In this case, it's asking us to solve for the temperature. So let's substitute in. The pressure is 5.60 atmospheres, so that's P. The volume is 12.0 liters. N is 4.00 moles. R, okay, well, R, again, we have two different R's that we can use. Which one do we want to use here? Well, to determine that, I have to look at my unit of pressure. My unit of pressure here is atmospheres, so then I need to use the R that has my unit of pressure in atmospheres. So that would be 0.0821 liter atmosphere over mole Kelvin. And then, of course, we're solving for T, so T will be there on the end. So then, to solve this, you can go ahead and divide by 4.00 times 0.0821, or you can go ahead and multiply those out. So I'm going to go ahead and multiply them out. 5.60 times 12.0. So on this side, we have 67.2, and that is atmospheres times liters. On this side, we have 4 times 0.0821, and that is 0.3284. And that is, notice our moles cancel out here, and we have liter atmosphere over K, and then that is going to be times our temperature. So then to solve this, I'm going to divide both sides by 0.3284. When I divide both sides by 0.3284, my 0.3284 cancels out, and on the right I have T, and on the left I have 67.2 divided by 0.3284. And I get 204.6285, so on and so forth. And again, this is going to be Kelvin. And then looking at our significant digits, we have 4.00 has 3, because remember I added the O's there, so we would have more than one significant digit there. 5.60 has 3, and 12.0 has 3. So we're going to do 3 significant digits here, so that's the 204. The 6 does change the 4 to a 5, so 205K would be our final answer here. Again, K is our unit of temperature. I know I don't have a lot of room to work this on this page. I think these are pretty much the same problems. I don't know how I ended up with two handouts that have the same problems. But anyway, I'm going to go ahead and turn over here and do these other two, just because I have more room to work them. So if you have your packet, or if you come and get your packet and you don't really have room to work them out here, then you can always work them out on this page. I think the big difference may be that one page has more problems than the other. No, they don't. I don't know how I ended up with both of those pages, because I think they both have the exact same problems. So anyway, I'm going to do it on this sheet now. So let's look at number 2. If I have an unknown quantity of gas at a pressure of 1.2 atmospheres, a volume of 31 liters, and a temperature of 87 Celsius, how many moles of gas do I have? Okay, so let's identify what they've given us and what they're asking us to find. A pressure of 1.2 atmospheres, so that's our P. A volume of 31 liters, so that's our V. A temperature of 87 degrees, that is our T. How many moles of gas do I have? So what are we solving for here? Which one of those in PIVNERT is moles? Well, that is going to be the N. So I'm solving for N. N is what I don't know. All right, so then another thing I see that I'm going to have to do here is I'm going to have to change my degrees Celsius to Kelvin. So 87 plus 273. 273 plus 87 is 360 K. Okay, so now I have my formula, PIVNERT. My P is 1.2 atmospheres. My V is 31 liters. My N is what I'm solving for. Okay, my R. Well, which R do I use? Well, I notice here again, my unit of pressure is in atmospheres, so this means I need to use the 0.0821. So 0.0821 liter atmosphere over mole Kelvin. And then times that by T, which we said was 360 K. Okay, my K's will cancel out. And on the left, I will have N times, and then we have 0.0821 times 360, which will give me 29.556, and that is liter atmosphere over mole, because the kelvins canceled out. And on the left, we have 1.2 times 31, which is 37.2, and that is liter atmosphere. Then, in order to solve for N, we're going to have to divide both sides by 29.556 liter atmosphere over mole. And then on this side, we're going to do the same thing, 29.556 liter atmosphere over mole. So the liter atmospheres cancel out, and our unit will be in moles. So now we're going to take our 37.2 divided by 29.556, and that gives us 1.2586279, and again, this is moles. Looking at our problem, it looks like all of our measurements have 2 significant digits, so we need to round this to 2 significant digits. That's the 1.2. The 5 does change the 2 to a 3, so that's 1.3, and again, our unit here, what we were solving for was N. Okay, so 1.3 moles if I have this pressure, this volume, and this temperature. Okay? One more problem. If I contain 3 moles of gas in a container with a volume of 60 liters and at a temperature of 400 K, what is the pressure inside the container? Okay, and I'm going to go ahead and put a decimal there so that that's not just one significant digit. And I'm going to go ahead and put a 3.00 there so that that's not just one significant digit, and put a decimal here because I want to have more than one significant digit. So moles, again, that is going to be my N. Liters is going to be my V. Notice our temperature is already in Kelvin, yay, that is going to be my T. And it asks me what is the pressure, so I'm solving for P. So again, I have my PV equals nRT. My P is what I'm solving for. My V is 60 liters, and I did add that decimal there. My N is 3.00 moles. I added that too, remember? The zeros, I should say. R. Okay, well, here's the question. What is the pressure inside the container? Well, which R do I use? Now, remember, the only difference between the two R's is the unit of pressure. So you can choose which R you want to use. Whichever R you use, that will be the unit of your answer at the end. So if I choose to use 0.0821, then the answer that I get will be pressure in atmospheres. If I choose to use the 8.31 kilopascals, then the pressure that I get at the end will be in kilopascals. So I'm going to go ahead and just use the 8.314 because we haven't used it yet. Again, you can choose which one you want to use. You choose whichever R you used will determine the unit of the pressure that you get in your answer. So the 8.314 kilopascal times liter over mole Kelvin or Kelvin mole. And then our temperature was 400 K. Again, the K's cancel out. And we have P times 60 liters is equal to, now let's multiply 3 times 8.314 equals times, I keep punching it in wrong, guys, 3 times 8.314 equals times 400 equals. And that gives me 9976.8. Again, my moles also cancel out, and what I have left is kilopascals times liters. And then to solve for P, I have to divide both sides by liters. So that cancels out. On the left, I will have P. On the right, the liters cancel out, and the unit that I have left is kilopascals. So 9976.8 divided by 60 gives me 166.28, in this case kilopascals. And then I have two significant digits because I added the zeros here, so that gives me 3.00 has 3, 400 with a decimal has 3, 60 with a decimal has 2. So I'm going to round this to two significant digits. So that means this 6 makes this a 7. So that would be 170 kilopascals would be the pressure. Again, I didn't have to use 8.314. I could have used 0.0821. If I had used 0.0821 liter atmosphere over mole Kelvin, then I would have gotten a different number here, and that would have been in atmospheres. So again, when it's asking you for pressure, if it said what is the pressure in atmospheres, then I would have to use 0.0821. But if it just asked me for the pressure, I can choose to use either one of those, and whichever one I use determines what my unit of pressure will be in my answer. Okay, I hope that makes sense to you.
If I can have your attention just to share a little bit of information with you. We are still working on getting student contact